really especially in this broad area, which is singularities, which was one of the main lectures of singularities in Mexico. And well, so I don't want to take more time to Santiago's talk. So for me, it's a pleasure to introduce our first speaker, Santiago López Medrano, from the Instituto de Matemáticas of UNAM in Mexico City. And he will talk about singularities of quadratic matrices.
Well, I've never really worked with Pepe, but anyway, Pepe has been very fundamental in my work. For more than 30 years, he's always been there to suggest things, to encourage, to help. First talk I gave about this mapping was a meeting in Mexico and Chapala, Mexico and Chapala, names become difficult. And it was very important for me to be invited to that meeting. And I thank him for many things over maybe 40 years. Oh, he was a student. I forgot that. He was in an auditorium bigger than this one, 400 students. He was one of them. I didn't notice him too much at the moment, but he was there. Okay, so I'm going to talk about this subject. This all started in a seminar where Pepe was and Javier Gomez-Mont, where Alberto gave a talk on the work by Camacho Goy-Perpales, and he said, here is a topological question for you. And he proposed that question. Recently he has confessed that he hoped that I had the answer for the following week. Well, I had the answer about a year later, and the details of the proof maybe 1 or 2 years more. And in a sense, I'm still working on that. I haven't answered his question. Okay, so the subject I study can be seen as follows. I take a quadratic, homogeneous quadratic map from Rn to Rk. Each component is a quadratic form, and they are the ones that are diagonal. They're very special, especially when they're more than two quadrics. They're very special, but still they're very important. One, because they're easier, so there are more methods to work with them. The other is because they do appear very much in the applications. Okay, so what I've been working on is the topology of the variety defined by this function, and of course this amounts to studying the intersection of this variety with the unit sphere. Sometimes I work on the deformations, the other inverse image, the other fibers, and there are some other objects related to them that have interest in topology. But when one looks at this question, one says everything should be known about them. I mean, for one quadratic form, we know everything. So somebody could have studied 2 quadratic forms. For one quadratic form, we know they can always be diagonalized. This is 2. They all can always be diagonalized. Series isolated singularities if and only if all the coefficients are non-zero. If sum of positive and order of negative, if they are all positive or negative, then the singularity is a single point, so there's nothing on the unit sphere. If not, there will be n of them which are p of them which are positive, which p of them which are negative. And here's a first principle we're going to use all the time. If we don't break the regularity condition, we don't change the topology of the manifold. So we can assume that they are all plus ones or minus ones, and then the equations are like this. They're not difficult to solve. You can add and subtract the equations to get these other two, and so it's obvious that for this normal form, y is the product of SP minus 1 cross SQ minus 1. Not that it is isomorphic, it is equal to. And in the same way, we can answer everything we want to know about this manifold, the formation of the fibers, halves of them. So, I will stop. Maybe someone had done something at least for k equals 2. For a while, I couldn't find anything until I found the work by Wall. I had done something of that kind, but some of it had been done before by Wall. And their interest was in real singularities and certain strata. So these mappings are two jets of mappings at a point where the rank is 0, so they're terribly unstable. And the diagonal ones are even more special. So from the point of view of all the functions, it's a very thin set and very unstable, and then the diagonal ones are a thin set inside that thin set. So one thing is there's some that shouldn't appear in mathematics, but they appear naturally in many places. As spaces of orbits, that's the origin, normal form of vector fields, non-commutative deformation of toric varieties. I can almost say that without blushing. I almost understand what that means. And then they're related to many other objects: polytopes, projective real complex varieties, toric and quasi-toric varieties, Artin concept of groups, foliations, complements of subspace arrangement, and polygon spaces. And they provide interesting examples of complex non-symplectic manifolds, vibrations of vectorial varieties, invariant manifolds, manifolds with group actions, generators of complex cobordism. These are not directly the ones I study, but these are certain quotients, etc. There are many places where this appears. There's also papers in numerical analysis that use these examples to test I don't know what. And there's also a rich theory known as toric topology that has produced many generalizations. Now there are some generalized moment angle complexes that are the fourth generation generalization of these guys, and they have implications in robotics. I think they should give new examples of stable mappings, as is this case of the handkerchief and C-square, but that is work to be done. Okay, and first work was done in the 80s. The first work was done in the 80s, and then not much happened for many years, but during the last 5 years, things started moving, and many problems were solved. This was generated on the one hand by the work by Bossi and Merseman on these manifolds for k greater than 2. On the other hand, on the work by Bari, Bendersky, Cohen, and Sam which did a very big generalization And functorial, it became a functorial object, but finally that's a very good thing for having a nice look, global look at what's happening. Okay, I will give a brief survey of the results. There's much material. I just gave a 16-hour course in the University of Saragossa, and what I can give you is just a brief survey. Okay, the first question is, what is Y empty and what is Y smooth? We know that only in the diagonal case, and it's very easy. When is it empty? Well, take a look at this. So we write it in equations like this. There are actually k equations, but the important part is are the coefficients of every coordinate with a unit sphere, and everything. The nice thing is that everything will depend on convexity properties of the AI, of the column coefficients. Okay. And the first answer is Z is empty if and only if the origin is not in the convex hull of the AI. We're in the Poincaré domain, the dynamicists would say. How do you prove that? Just stare at the equations. The solution of these equations gives you immediately a combination of the convex combination of the AI that gives 0. So that's it. A more subtle condition is when is it smooth? It's smooth if and only if no collection of k columns. So you take that matrix of the AI, take a k by k matrix, and you want that the origin is not in the convex hull. This is known as weak hyperbolicity. So we take k equals 2. You think the condition is as follows. This is weak. This satisfies weak hyperbolicity. Something happened with my A's. We have corrected them now.
Excuse me, what is Z? What is Z?
Z is the
Is it Y? Is Y?
Y. Yes. Z is Y and the A's. A's, the lambdas are A's. We corrected that yesterday, but something happened. Okay. So in this case, we're in the k equals 2, we're in the plane. In this case, the origin is in the convex hull of 2 of them. That meaning the line. It doesn't matter if there are 2 points that are linearly dependent. You could have a multiple of lambda 1 here, and that's no problem for smoothness. One could have even twice, and we do that many times. Take the lambda 1 twice as a coefficient, and that doesn't matter. If you ask that every k of them are linearly independent, that is called hyperbolicity. And that's very important in dynamical systems, but you want to see and sometimes in this questions it's important too, but when you want to see the topology of Y, it doesn't matter, it's the weak hyperbolicity. I have another way of saying this, and it's very important to introduce the polytope. If you take, there's a C2 to the n action on Z. Z is usually when it's diagonal, that's it. But when it's diagonal like this, it's usually called Z. And I didn't check all this. I put all Y's here, but I forgot some. Okay, there's a C2 to the n action on space manifold. The equations all have xi to the square, so you can change every coefficient as you wish, and that gives you an action of C2 to the n. The quotient, what's the quotient? The quotient that every point is equivalent to one that has all coordinates non-negative. a change of signs. So the quotient is just the intersection of zy, this yc, with the first ortho, which is given by, again, by the equations, but with inequalities on the x side. And you can change the coordinates easily to make it linear. And so the quotient is this polytope. And the polytope determines the whole topology of the manifold. You see here I try to draw. Here I am in R3. I drew the polytope. The polytope in this case consists of just this interval. And if I reflect on all hyperplanes, according to hyperplanes, I get this. In this case, I get these two circles. They would be circles. I have the coordinates, the old coordinates, and can it be seen? Yes. And so the polytope has all the information. The polytope knows the manifold and knows the action and everything. And then can be seen that weak hyperorbitalicity is equivalent to the transversality of P at all planes. Here we have this P is transversal to all subspaces, say to the stratified space of all positive subspaces, and the variety manifold. Here we have an example where it is not transversal. If the interval is like this, it is not transversal to this coordinate subspace. And if you reflect now, then you get this singular object. I'll try to say more about that at the very end. I used to say that with WH is equivalent to the fact that the polytope is simple, but it is not. Here's an example of that. It is a simple polytope. That's the definition. But it's a simple polytope, but it's not replaced. No weak hyperbolicity. Okay, how do we study them today? There are several operations that you can do among them. You can take products. You have two of these. You can just add the equations one after the other. It's not the same because you don't have the equation of the sphere. You have two sub-equations, but you can do the inverse operation that we did before to get the equation of the sphere and the sum of the two and the difference of the two, and it gets back the form of the ones we're considering. We can intersect with a half space or with a hyperplane. This is very important operation. You take that variable that's diagonalized. It only appears as a square, and then you add another new variable with the same coefficients. And that turns out to be a very important operation. Or you can take two of the equations. You think of them as a real and complex, real and imaginary parts, and you add double square to them. That is in the diagonal case. And there's also a very important operation is when you truncate the vertex of the polytope. Any polytope can be realized in this way, and any simple polytope can be realized in the weak hyperbolicity case. And so you can do things to the polytope, and let's see what happens to the manifold. The most important is truncating the vertex of the polytope. Okay, and this has geometry. Y plus is a manifold with boundary Y0. Y prime is an open book with leaf Y plus and binding Y0. If you make Y prime cross, it's a manifold with boundary Y. So Y is always the boundary of the manifold. And cutting a vertex, it amounts to taking the sum of two copies of Y and adding a number of copies of S1 cross D minus 1. Here D is the D is the dimension of the manifold, original manifold Y. So by looking not at the single manifold, all the cases and all the many relations among them is the way that we finally solve many of the questions. Okay, and the main result we have is that in many cases Y is a connected sum of spheres products of pairs. You take a pair of spheres, take their product that adds up to dimension D, and then take the connected sum of many of those. And how do you prove that? You prove that this operation, such as define, preserve, connected, this type of connected sums. Not always, but under certain hypotheses, you can prove that they preserve that type of connected sums. Then you look at some the simplest of all cases. They're highly connected and they can be treated specially, and then you go up in dimension by using the operations to get all the cases. And these basic varieties correspond to the polytopes that are called neighborly polytopes. Neighborly means that you take facets up to you take two facets of dimension almost half of the dimension of the polytope, they intersect. Almost every facet intersects with every other one. Okay, can see that. But there are these polytopes, and experts in the field think most of the polytopes are like this. That's a feeling, that's some probabilistic ideas and estimates, but they think that most polytopes are like this. So we think now that most of the manifolds Y are like this, because you have these cases to begin with, and then you go up with these operations and you get all many new you have these junctions like the roots, infinitely many roots, almost all polytopes, and up from them there are trees branching indefinitely. So I think most of the intersections of quadrants in the diagonal case are this type of connected sums. The proof of all these facts uses some interesting topology here. Y, the manifold we're studying, is the boundary of 1 plus. Remember, Y prime will add a new variable, and then plus, we restrict that variable to be positive. And it turns out that all the homology classes in Y are spherical, either in the basic examples or in the induction step. And all the classes of Y prime come from the boundary. This is I've never seen it written, but it's a kind of principal differential topology. If you want to know a manifold, look for something in bounds. In Spanish we say, dime a quién bordeas y te diré quién eres. Okay, for example, homotopy spheres have nothing, no poles, nothing. It's like an ordinary sphere, no matter how much you look at them. Cannot tell the difference from a real normal sphere. There's no way. But if you find the manifold in bounds, then looking at the manifold in bounds, you know that the sphere is you can, depending on the manifold in bounds, you can tell that the manifold is a standard sphere or is an exotic sphere, etc. That's how the first ones were discovered. bounded manifold.
Micrófono.
With this, having this, you know pretty much what is this manifold, because you have represented all the homology classes by spheres, and that's enough to say it's a connected sum of products like this under certain hypotheses, especially dimension and simply connectedness. If not, it becomes complicated. But we will go into that part. Okay, so these are general theorems for any number of equations, but for two equations we have complete results. You have a variety y, diagonal or not diagonal, and could be empty, but if it's not, then these are the possibilities. It is the unit tangent bundle of a sphere. That's a case everybody knows. It's the what's called cipher variety. There's an equation, sum of zi squared equals 0. That's the equation for the unit tangent bundle of the sphere. Can be the product of two spheres. That is when you add a variable, the tangent bundle becomes trivial and you get the product of spheres. You can have the product of three spheres. That's very easy. It's again an operation just like the one we saw before. And the interesting case is that it is the connected sum of sphere products. This is all you can have for the case equals 2. And if you're given a y, there's a way to tell you in which case it falls, and what are the spheres in all cases, what are the dimensions of the spheres, and how many summas you get here. And to get the precise result of how many spheres and which dimensions, you have to compute the homology, and this is done by interesting computation of the homology using a splitting of the homology of the manifold in terms of the combinatorics of P, which is valid for every K. What we don't have for every K is a normal form to which we can reduce the many things were for any K, but we cannot tell how many cases are there. In the recent development of Barry-Vendersky co-Gittler, there's something very interesting, which is that the suspension of Y, it is the suspension of Y that splits as a wedge of spaces. So the composition of the cohomology can be seen geometrically as a decomposition, not of the space itself, but as a decomposition of the suspension, and that is a very interesting way of looking at it. Okay, so we have this special quadrics, homogeneous quadrics in Rn, and in some of them diagonal, but I think that this has consequences even for a classical question, the study of intersection of real projective quadrics. If you take the Y and you projectivize it, you get a projective intersection of projective quadrics in projective space. And all of them appear like this, because you can take the equations in Sn are just the equations that we have been using. And these are more difficult to study. The main problem is questions of orientability, and the computations get very complicated. I'll say something about that later in a complex version. And seems very difficult to say the topology of all the intersections of two quadrants. But it gives us some information about this question. To start with, I can tell you for the intersection of two quadrics, two projective quadrics in Rn, smooth complete intersections of two real quadratics in Rn, I can tell you what the covering space is, what the double covering in the sphere. And then there's a little trick by Johann Mersemann that shows that all of our intersections of quadrics are actually projective too. It's very simple. You take the y, we know that we can make products. We can take product with a sphere, we can take product with a zero. That is another intersections of quadrics of the same type. And then we projectivize. When you projectivize, y cross S0 divided by S0 is y, obviously, and with y. So every one of our manifolds is an intersection of projective quadrics. So this gives information. For example, now we know there are smooth intersections of two quadrics in RBN which are diffeomorphic to these products. There are smooth intersections of three quadrics in RBN which are diffeomorphic to any of these objects we mentioned before. And for every k greater than 2, there are many, many smooth intersections of k quadrics which are diffeomorphic to connected sums of sphere products. And many other nice things. This is about classical projective real geometry. Well, the thing is that these are project intersections such that the double covering of the sphere is trivial. So, could be they're not interesting. But anyway, I think in this subject, I don't know very much. There doesn't seem to be there too much information about it. But I look at it as a starting point for studying other cases. But for k equals 2, we will all have these examples. They all have free homology. They're very simple. But for k equals 3, it can be less simple. Can be a product of connected zone of a product of a surface and a sphere, and new interesting topological types. The for k equals more than 3. You get all that, but then it gets messy. You can have huge torsion groups with all kinds of P groups for many P's, homology in homology, and they have triple massive products, so they are not formal. Also, a thing we have done is to consider the half manifold, y plus, and the deformations, and it seems that for the machinery we have done for k equals 2 works very well for studying many variants such as this. There are open book structures, but other questions seem to require new methods. Well, we just mentioned one, the projective ones. I thought the next step, the projective ones. No, it's too complicated. Let me tell you a little, let me tell you about what are called moment angle manifolds. We have this variety y defined by these equations, but we can also consider the variety y z in z to the n from the holomorphic point of view. These are holomorphic equations. This is not an algebraic variety, and but these ones are the origin, at least from my point of view, of all the things. The first question was to study by Alberto was to study these guys. So we had strange names for them. but now they're called moment-angle manifolds. That's why the toric topologists call them, and why not? We call it that way. And this guy, from the topological point of view, this guy is just one of the ones above. This is xi squared plus yi squared. So it's a sum of real squares with duplicate coefficients. So there's nothing new here. But they have interesting properties. First, now there's an action of the torus with the same quotient. And when K is even, it turns out that the projectivizations admit a complex structure. These are not complex as manifolds of complex projective space. They have those horrible equations, but they do inherit a complex structure. Thing is, the dynamical system that's sitting behind gives a foliation, and these manifolds are transferred to that foliation, and that's enough. Holomorphic foliation, and that's enough to get a complex structure. So there's the question now of what are these projectivizations. And then, well, having solved all the other problems, I decided to go to these ones. A long time ago with Alberto, we had the first cases, and there are the quotients of the triple products. Sometimes they are products, sometimes no. Now they are called projective products. You take a product of spheres and you divide by a diagonal action. And so these are complicated by themselves, triple products. But when you have a connected sum of sphere bundles, if you look at the projectivization in the simplest case, and you go up a little bit, you have the topology is sphere bundle over CPD minus 1, a kind of Klein bubble, and some generalized Klein bubble, and some products of spheres, like informed products of two spheres added to this. Optimistic a conjecture. Well, so far all my optimistic conjectures have worked, but not this one. There's you don't have to go far to find an example. As you find dimension 17 is far. There's a manifold Y, which is sum of 5 copies of S7 times S10, and the cohomology ring is as follows. I didn't put the 0 here. The 0 it's connected, so it's generating. Then nothing in this odd dimensions. Then this element is the Euler class of the manifold that lies in the sphere, projects into the projectivization, and this is the Euler class of that manifold. So you have this. It goes up to E3. We know for certain theoretical reasons that e to the 4th is 0. But then in dimension 7 you have four generators. A1, A2, A3, A4, and it turns out that E multiplied for this generator lives in the next dimension, and the product of the A's are like this. Product of these go up to the E squared Y. There's an element in dimension 10, and it goes all the way. So there are products all over the place, and that's not a connected sum. And don't be split as a connected sum. So I'm stuck there. I don't know. I'm incurably optimistic, and I think I'm going to find out what manifold is this. Well, I did a similar search at the beginning of my work. When we got the triple products were found very easily, and then the next case was impossible to tell which the variety was. I started a search like this, and after some time, there was no Google at that time, so you had to take these big volumes of mathematical reviews, look at the different sections for each month about manifolds with the group actions, and after a while, wow, there was my manifold was there somewhere. A work by McGavran. So I'm still looking for this. If somebody has seen it, please let me know. Okay. Another thing recently that hasn't worked too well is that Alberto and his student Yadira started studying the possibility of having contact structures on these manifolds, on the moment-angled manifolds. One would have thought that there are not, in our manifolds, in the even-dimensional ones, there's hardly ever there are cases, but the generalities that there are no symplectic structures. So how can one expect that there are symplectic contact structures on the off-dimensional ones? And it turns out that there are many complex structures, because all the connected sums of sphere products have a contact structure. This is due to, well, it's not stated, but it follows. There's a work by Eliashberg that shows that a product of two spheres of different parity has a contact structure.
Natural one. Natural one.
Natural one, I don't know. It has one, but it's not natural, but it's a very good theory. And then there's this lady Meckert that showed that connected sum of contact manifolds is a contact manifold. So there are many. It's possible that all the other ones have contact structure. And what Alberto and Yadira did was they couldn't find the structure of the manifold, but in some non-diagonal versions of them. If you add complex squares like in the cases before, you get things with contact structure. So you take one of these moment-angled manifolds, and you add squares to get non-diagonal things, and those have contact structure. That's what he proves. Using some deep results about the heat equation. Anyway, so the idea was, so there are all these new contact structures. Well, we don't know here. I came up to spoil the party because from the ones they have, then the ones I can tell what the topology is are connected some sphere products. These are not new contact structures. Well, they never been stated, but it follows from these results. And the other ones, they look harder. That's another tough problem we're dealing with. There's another unsolved question. In the first examples, with k equals 2, it is it is useful to write them in terms of roots of unity. The coefficients can be used of unity with multiplicity. And also when you, for constructing surfaces as intersections of quadrics, it is useful to look for the intersection where the polygon is also symmetric. So that gives you two extremes of interesting manifolds which have cyclic symmetry, but actually dihedral symmetry. So can we find, those are the manifolds with low codimension, and the manifolds with big codimension that have been constructed. Now the question is, it's easy to write what should be in between, and you get some examples where the manifold or the coefficients are taken out of this van der Waals matrix. Here, rho is a primitive root of unity. So what one has to check is if these intersections of quadrics satisfy weak hyperbolicity or hyperbolicity or strong hyperbolicity. There are many variants, and that depends on properties of the van der Waals matrix with the roots of unity. We would be in the best of worlds if all the squares of matrices of any size of these matrices were non-singular. But that's not true. It can only happen when n is prime. So the conjecture now is that it's true for n prime that all minors of that van der Waals matrix are non-zero. There's also when n is composite, the minor can be non-zero, but it turns out in numerical examples that if a minor is zero, the complementary minor you take certain columns and rows, the complementary you take the other columns and the other rows, and there seems to be an interesting duality between these two. For example, in the case we know, we have the surfaces and dimension 2 and the intersections of two quadrants of dimension 2 in the sphere. And then the coefficients of one are the polytope of the second one. And the coefficients of the second one are the polytope of the first one. It's a strange duality. Looks very nice, but we don't know. Just last week, Matthias Franz gave a new idea of how to attack this problem. We're working on this, but it still looks far away. So that's another question. Another question, which is still open, is to determine which surfaces may appear as our intersection of quadrants. In the diagonal case, the answer was no to Gibbs. He wrote, when I told him of my quadrants, he wrote in a napkin in a cafeteria. He wrote these equations that gave all the surfaces. So that's for the diagonal case. It's well known, and then these surfaces coincide with the surfaces with the genera of these surfaces coincides with those of the curves, complex projective curves that are complete intersections of complex quadrants. This is a work by some Chilean professors, González, Rodriguez, generalized Hamburg curves. Hamburg did the case 5, Genus 5 long ago, and they studied this from the point of view of Riemann surfaces, and they get exactly the same genera. In the deniable case, we don't have complete result, but we can construct a family of surfaces, and the genera coincide up to an experimental error or two with the genera of the projective complex curves that are complete intersections of complex quadrics. So here's a mystery for you. Is that just a coincidence? Or there's something deep behind this? And the general problem, what are all the genera? Have we obtained all the genera, or we need to look more for them? Finally, there's a question of Pepe, that Pepe had several times the last 30 years. What happens if we know, if we have weak hyperbolas, if the manifold is smooth? Can it happen that the manifold is smooth, or it is a topological manifold if the weak hyperbolicity doesn't hold? Well, it is not true, but there are silly examples that we can figure out. For example, if you have the equations of a nice intersection of quadrics, and you add 0, 0, 0, 0, 0, you get something that's degenerate, but it's still smooth. So you have to remove some trivial cases like this, and it seems that it should work. The answer is given in this drawing. See, if you have the polytope, you reflect it in all faces, and then you get something that's not a manifold. Looks simple. It should be a linear algebra question. Really, almost linear algebra question. And I had hoped that my talk would be on the second week, and that I would have time to think about this problem. But no such luck. Anyway, thanks to the organizers.
Are there any questions?
As you said, one way to study a manifold is by looking at another one that it bounds. Now, say in the classical case, say if you go take map into R2, which is somehow simple. In that case, you have the critical values give you lines passing through the origin. And so it splits the plane into sectors. And each sector consists of regular values. And so you have the corresponding fibers, which are somehow like Milnor fibers in a way. And I know that you study somehow how the topology of those fibers changes as you change the sector. Can you say anything?
Well, yes, but I haven't I haven't given the background for that.
Yeah.
So you have these points, you draw the polygon generated by those points and the sections. Then, what I can say in those cases is what is the topology in each of the sectors. And how it changes. That was studied in a way by Bosio Merseman too. And they have some very interesting things about that haven't been explored. They have a concept of cobordism of polytopes that I think should be very interesting even for polytope theory, but that has not been developed. And one of the parts is
This question.
No. Oh, you tell me the question. One of the cases is cutting the vertex of the polytope. That's one of the possibilities. truncating the polytope. That's one of the possibilities they have. And that's the one I studied and was very useful. The others are more complicated. The other changes in the polytope involve cutting and gluing back again. So why did they change? I don't know. The simplest case, if you're outside the polygon, you get empty. When you enter the polygon, that's a pentagon, that becomes 4 spheres, 8 spheres. And all of there's nothing, and all of a sudden there are 4 spheres. And the spheres start joining, just sending fingers, and you get 2 tori. And then the tori send fingers to each other, and you get the surface of genus 5. So every change is not just a single surgery. It's very complicated because of the symmetries of the whole thing.
Any other question? Okay, let's thank Santiago again. The coffee break is outside just in the auditorium.
Speak here is big, it will not be mathematical conference talk at all. On the contrary, I will show some pictures and I will show some presents, some gifts to you. The first one is a gift from Santiago to Pepe. So there it is.
I just say a word for people who were not here in the first talk, in the first week, or in the first talk. I talked about these intersections of quadrics. So you have the intersection of K diagonal quadrics in Rn and intersected with the unit sphere. And I've been working on this for the last 30 years. And sometime, maybe almost 30 years ago, Pepe asked me about the following question. There's this condition, which I explained here. That's the condition for the regularity of this system. And Pepe asked me several times over the years whether this condition was necessarily sufficient to have a smooth manifold. So that's a condition for C to be of smooth variety, and the question was in case this condition failed, you always have some kind of singularity. Okay, when I planning to come here, one of my plans was to give in my talk an answer to Pepe's question as a present. But then the organizing committee had other plans for me. They put me as the first speaker, so I didn't have time to solve this question. And then secondly, they organized so many nice talks that it was very, very hard to work during the talks. So after some time, I finally have an answer for Pepe. So the answer is that it may happen that the manifold is smooth, but only some very specific questions. When there are really not enough, these are not really K equations, but the rank is less, or where the varieties containing coordinate happen. So it's really either the K is smaller or the N is smaller than it should be. And then under these conditions, it turns out that if the weak hyperbolicity condition fails, then there's a critical point where the link is not even a homology sphere. And that's it.
Thank you. Well, thank you, Santiago. No, just continue.